Okay, so I think you basically refer the previous lecture note. So in that lecture note, we discuss about the transformation of this continuous signal into discrete. So let's assume like we have kind of a signal xt, so which is basically in continuous time domain, and we need to convert it to xn. So what we basically did was, so we just convert, we use this substitution t. So this t basically defined as the sampling period, sampling period. So n is kind of an integer value. So this is an integer value. So we use this substitution t equals nt, and then you can basically convert any kind of a continuous signal, which is something like that. So this is your xt, and we take the discrete samples of this continuous signal. For example, if you substitute n equals like 0, 1, 2, 3 and so on, so we can basically get t equals 0, t, 2t, 3t and so on. So these are the t values which we basically capture the sample. So this is like so we have like this is 0, so then this is t, so this is 2t, so this is 3t, and these are the samples which we are referring. So these, so then we basically select the reasonable number of samples which basically represent the continuous signal. So this is actually x0, this is actually xt, this is x2t, this is x3t. So from this continuous signal xt, so we capture the certain set of samples using a kind of a sampling period. So the sampling period is the duration between these consecutive samples. So this is the sampling period. So if you want, we can add a subscript ts. So this is the sampling period. So then what we simply do here is we pick the samples at every t seconds. So initially we take the samples at 0, t equals 0, then we take the samples at t equals capital T, then pick the samples at t equals 2t, 3t and so on up to the whatever the range we define for t. Maybe from 0 to infinity or minus infinity to plus infinity. So depending on the range of t in this continuous signal, so we basically capture the samples of this continuous signal at a rate of ts. So then so this x0 basically represent using x0 in xt is actually x1, x2 and x3. So if basically this t s is a constant for this process. So if you are performing a sampling, so we can set that sampling period to a certain value. So it's a constant for the entire process. So then what we can simply do is, so we can represent this discrete samples by assuming that Ts is constant. We can simply use this index n. So depending on the index n, we can basically represent the samples at t, samples at 2t, 3t, like that. So then we basically have x0, x1, x2, x3 and so on. So these are the values of n. So this is n equals 0, 1, 2 and 3. If you map it to this xt, so we basically capture x0, xt, x2t and x3t. So these are the samples we are capturing here. So these are the samples we basically capture. So the corresponding n values are there. So then we can easily represent this discrete signal using this particular values x0, x1, x2, and so on. So these are giving the index of n, and this is the sampling period. So this is the simple process of converting a kind of a continuous signal into discrete. So this is continuous, so this is continuous, and this is discrete. So hope it's clear. So the next thing actually, like for example, you have a kind of a simple signal cos 2 phi ft plus theta. So here f is the frequency in continuous domain. So xt is a continuous signal. So we took a simple example as a cosine function. So cos 2 phi capital F t plus theta. So this is your domain. So this is a kind of a continuous signal, and capital F represent the frequency of the continuous domain signal. And similarly, we can define capital omega, which is actually angular frequency, again in continuous domain. Okay. So we basically define two parameters, capital F and capital omega, which are basically in continuous domain. So one is representing the frequency of the signal, the other one is representing the angular frequency of the signal. So by looking at this one, we can simply claim that this capital omega equals to phi capital F. So this is the angular frequency radians per second. This is the frequency hertz. So this is very fundamental equation. Omega equals 2 phi. Okay, so now we basically need to convert this into discrete form. So now we need to convert it into a discrete form. So how do you convert it into discrete form? Use this substitution. So Ts is the sampling period and n is a kind of integer capturing this set of samples. So if once you substitute this into this above equation, we basically get this cos 2 phi f. Instead of t, we can put nts plus theta. So this Ts is the sampling period. What about sampling frequency? Fs. This is just the reciprocal of this Ts. So this is actually sampling frequency. Okay. Sampling frequency. How many samples per second? Sampling frequency. So here it's like how many cycles per second. So it becomes how many samples per second. So sampling frequency. So this is sampling period, and this is sampling frequency. So then we can rewrite this expression cos 2 phi f, and Ts can be replaced with 1 over Fs. So then this becomes Fs n plus theta. So now, so this continuous signal which is mapping T domain is simply transformed into N domain. So see, so here we have T, here we have N. So then this becomes a kind of a discrete signal Xn. So by looking at this component, we can simply define two parameters for the discrete domain as well. So one is the discrete frequency. So this is actually frequency in discrete domain. So which is equals to, so this is the frequency which we are referring. So if we consider this one, so in between 2 phi and t, we have this frequency component. So if you observe this, so this is 2 phi and this is n. So this in between these two parameters, this is the frequency. So then we can simply say that f equals f divided by fs. So this is the frequency in continuous domain. If you divide that frequency in continuous domain with sampling frequency, you can easily get the corresponding discrete domain frequency. In certain textbooks, this is referred as normalized frequency. Okay. So either it's a normalized frequency or the frequency in discrete domain. So it's easily can be computed by dividing the exact analog or the continuous domain frequency by sampling period. So similarly, we can bring another variable simple omega. So this is angular frequency in discrete domain. Okay. So if you want, you can get expression omega is actually 2 phi f. Okay. So this is the mapping between this continuous domain and discrete domain. So hope it's clear. Any questions? So we basically define two set of quantities for the continuous signals and discrete signals. So capital F and omega gives the frequency and angular frequency in continuous domain, and simple F and simple omega gives the corresponding discrete frequency and discrete angular frequencies. So how do you convert it? So it's just a simple substitution, T equals NTS. Okay. Now, here, so this frequency basically is in between plus infinity and minus infinity. So this omega also in between plus infinity and minus infinity. So you can select whatever the frequency in continuous domain. It's a frequency. So it may be 0 hertz, 100 hertz, 1000 hertz, 1 kilohertz, 10 megahertz. Similarly, mathematically, we can define the minus frequencies as well. So this frequency, this capital F, which is a continuous domain frequency, basically lie between minus infinity and plus infinity. Similarly, this angular frequency also in between plus infinity and minus infinity. For example, if you substitute plus infinity and minus infinity, definitely the angular frequency also in between minus infinity and plus infinity. So this is the range of this continuous domain quantities. So they basically lie in between minus infinity and plus infinity. So now, so we need to find the domain of the simple f and capital omega. So how do we get it? Okay, so let's think about this discrete signal xn equal cos omega naught n plus theta. So we have a kind of a specific angular frequency. So this is the angular frequency defined in discrete domain. So let's see what happens to the signal if we increase our angular frequency by 2π. So what we are planning to do is, so this original signal has a certain angular frequency which is basically represented by omega naught. If you basically change your angular frequency to omega naught plus 2π, what happens to the signal? Cos. So instead of omega naught, we have this omega naught 2π, omega naught plus 2π into n plus theta. So if you further simplify, this is cos omega naught n plus 2π n plus theta. So we know that, so this cos theta and cos 2π n plus theta are equal. Okay, so this is a kind of a fundamental trigonometric concept. Cos theta and cos 2π n plus theta are both same. So this means actually multiples of 2π's. So this is cos theta, and the if you take the multiples of cos, so it basically comes to the same angle. So if you plot it like this, so this is your theta. So 2π plus theta means so 1tan plus theta. So it's simply lie on the same. So this is 2π plus theta. 4π plus theta. So we basically have 2 tans and commit. So this is 4π plus theta. So likewise, any multiples of 2π, it gives the same angle. So this is basically equals to the original function. So from this we can claim that this is equals to cos omega naught n plus theta. So which means your angular frequency, so this omega naught is basically periodic over 2π. Because so we discussed this periodicity in previous sessions. So by looking at this derivation, we can simply claim that omega naught is basically periodic over 2π. So then we can define the range for the omega. So either it may be like between 2π and 0, or else one can define omega is between +5 and -5. So here also the period is 2π, here also the period is 2π. So in general, we can simply say that the angular frequency of this discrete domain is periodic over 2π. Okay. So now from this we can claim, so the period of this or the range of this omega is this. Okay, so we'll map it to the frequency. What happens? So we know that omega is in between +5 and -5. So we know that this omega can be represented using 2π. So then it becomes -π. This is 2πf in between 5. So if you divide the entire expression by 2π, so it's basically -half f plus half. So then the normalized frequency, so normalized frequency or the frequency in discrete domain is basically lie between -half and +half. So if you take this one, so it's like f between 1 and 0. So the normalized frequency, that's why we simply say that it's normalized. Normalized means the maximum value would be 1. So normalized frequency is in between. So this is the range most of the textbooks are referring. So that's why I'm sticking into that one. So then it's easy to discuss some examples. So, whatever the concept is, the angular frequency in discrete domain is periodic over 2 phi. So then the range of this angular frequency is either minus phi to plus phi or 0 to 2 phi. So I'm sticking into this and then claim that the frequency in discrete domain is basically lie between minus one half and plus half. Okay, so then from this what we can see, we found that capital F, so the frequency in continuous domain is basically lie between plus infinity and minus infinity. So this is the continuous signal. But we map and derive a discrete signal, and the frequency in discrete signal is basically in between this range. So this is discrete. Okay, what is actually happening here? Can somebody tell me about what's the real meaning of this one? Anyone have an idea? No? So this is actually, so here, so the frequency can be basically any value in between minus infinity and plus infinity. Once you convert it into a discrete form, the discrete frequency is basically in between minus half and plus half. So it means, so whatever the frequency component in this continuous domain is basically mapped to this range. So if you draw it, so this is the capital F. So this is the simple. So this entire domain is basically mapped to this. It's mapped to this range. It means, so it doesn't say that this minus infinity is simply mapped to minus half and plus infinity is just mapped to plus half. So what happens here is, so this is kind of a folding arrangement. So for example, so if you, so we will look into that later. So what I want to highlight here is there may be multiple frequencies in continuous domain mapping to the same discrete frequency. Okay, so we'll go one by one, then you may understand that what I want to highlight here is, so as a conclusion, now we found that F is basically in between plus infinity and minus infinity. Similarly, capital omega also in the same range. And simple omega is in between plus phi and minus 5, f is between plus half and minus half. So this is the important information. We can pick it from here. Okay. Any questions? No. Okay. So then we'll go into this. Yes. Okay. So what I want here is now I am comparing continuous signal and discrete signal. So we know that how to convert this continuous into discrete. We just substitute this, nothing else. So, but what happens with this substitution is here. So we have this two parameters in continuous domain. So I use this capital F and capital omega to represent the frequency and angular frequency in continuous domain. So after this substitution, this basically convert into simple F and simple omega. So these quantities are defined for the discrete domain. So we have discrete frequency and discrete angular frequency, which are in simple letters, and continuous frequency and continuous domain frequency and angular frequency in capital letters. Now we need to find the relationship between these two quantities once you apply this substitution. So we basically have a continuous signal. So we have this kind of a signal and we convert into this kind of a model. So here we have a kind of a set of frequency and angular frequency defined for the continuous domain. Similarly, for this kind of a discrete signal also, we can define a frequency and angular frequency. With this substitution, so what we want to see is what happens to these signals. So then we claim that whether we have infinite range for these two quantities, this is limited to, so this first parameter, so this is basically limited to minus half to plus half. And this is basically limited to minus 5 to plus 5. So that's the real thing happen inside this entire sampling process. Once you convert this continuous signal into a kind of a discrete signal, so we have this. So if I explain it using one example, so let's think of this sinusoid. Okay. So if we take 5 samples from this sinusoidal cycle, so I'll take these samples. So I'll take this one and the peak value, this and this. Okay. So then if you convert it to the discrete form, so we have this kind of a signal. We have one sample here and one sample here, one here, one here. So this is the discrete form if you take 5 samples per cycle. So this is 5 samples per cycle. So we basically ended up with these 5 samples. So we take this samples sampling period is T by 4. So this entire process is T, this is T by 4. Okay. Now let's think about this signal. Okay. So there may be a signal like this. So what I want to highlight here is there is another signal having a higher frequency than this signal, which is highlighted in this black. So this blue signal is having a higher frequency, and again we pick the samples at this point for the blue signal as well. Okay, so we have one frequency F1 which is mapped to this black line, and we have another higher frequency F2 which is mapped to this blue line, and we take the samples at a rate of this. We pick the 5 samples out of this entire cycle set. So then if you pick these samples for this blue signal, it's again like this. So this is the discrete signal for this F2, and this is the signal for F1. So then if you simply think of these discrete signals only, so by looking at these two discrete signals corresponding to F1 and F2, they basically is exactly same. But if you map it to this analog domain, if you map this signal into analog domain, so we realize that, so this red, this discrete signal in which is in red is mapped to this black signal which has a analog frequency of F1, and the discrete signal which is highlighted in green is basically mapped to this analog continuous sinusoidal signal which is in blue, has a frequency of F2. But both are exactly same in discrete domain, but once you map it to the continuous domain, so they are basically having two different frequencies. So then it means if you do a kind of a sampling for this black signal and blue signal with different sampling periods, ultimately we will end up with the same discrete signal or same pattern in discrete domain. So we cannot recognize those two signals. Those two means this one and this one. So we cannot recognize these two signals in discrete domain where it's basically derived from, whether it's come from this black line or blue line. So that's the case. So it means there may be certain set of frequency component in analog signal or the continuous domain which are basically mapped to a same discrete signal, or which are basically generate the same discrete signal. So these two signals are exactly same. So this one and this one, but they have two different sampling frequencies. But they basically, if you generate these two signals, you cannot easily recognize so whether it's come from black line or blue line. So that's the issue. So it means, so analog frequency or the continuous domain, we have infinite set of frequency component, but certain set of frequency component are mapped to a single frequency, single value in discrete domain depending on the selection of TS. So it means like ultimately you will ended up with the same discrete signal, which is basically derived from different signals in continuous domain having different frequencies. So that's why we have these two different frequency component, capital F and omega representing the analog or the continuous domain, and simple F and simple omega explain the frequency and angular frequency in discrete domain. So what we clearly identify here is whether this range of this continuous domain quantities are between minus infinity and plus infinity. We basically pack those frequencies to a range values in between minus half and plus half. So if we practically explain the scenario, we may get a same discrete signal for multiple or for the set of continuous signals having different values of f. So this is the simple example. So we can discuss couple of examples, then you may realize what basically we are referring here. Yes. Okay. Yes. So did you get a kind of a clear picture about this? Okay. Yes. Now, so we found that this is the range for discrete domain. So this is discrete domain. So f is in between plus half and minus half, and omega is in between plus 5 and minus 1. Okay. So it means like the f max is half and omega max is plus 1. Okay. Okay. From this, so we know that f is actually, this f is actually capital F divided by fs. So the capital F is the frequency in continuous domain and fs is the sampling frequency. If you substitute it to here, so we can simply claim that, so f over fs equals half. So then fs equals 2 times f max. So from here we can argue that the maximum frequency in discrete domain would be half. So if you substitute this capital F divided by Fs for simple f, we can simply argue that the maximum frequency in continuous domain divided by the sampling frequency, which is basically constant for this process, is basically gives half. So from this, we can claim that the sampling frequency would be 2 times f max. So this is the, in some cases, this is specified as Nyquist theorem, or some textbooks simply refer as this is sampling theorem. Whatever, so the ultimate core is you basically take your sampling frequency of any continuous signal at least 2 times the maximum frequency of the signal. For example, so we have this kind of a random signal. So this is a kind of a random signal xt. If you apply Fourier analysis, we can come across the how many frequency component basically inside this xt. If you apply the Fourier analysis, we can simply capture the frequency component inside this one. So there may be frequency of f0, there may be frequency of f1, f2, and so on. So then based on that, we can basically find out what is the maximum frequency. So these are capital F. So what is the maximum frequency component at the inside this xt? So we have a kind of a random signal xt. So from Fourier analysis, we can transform this continuous signal into infinite set of frequency components. So from that, we can basically identify whether this 10 Hertz signal is there, 20 Hertz signal is there, 30 Hertz, 45, kind of. So once you apply Fourier analysis, you can simply recognize what are the frequency components contributing to xt. From that, we can basically identify what is the maximum frequency component embedded inside this xt. Whether it's a 10 kilohertz or 10 megahertz or 35 kilohertz or whatever. So then if you know that one, if you know this maximum frequency, so you can decide the sampling frequency to sample this xt without showing any distortion. Okay. So let's assume like this xt, if you apply Fourier analysis, so we found that there's a 0 frequency component, 10 Hertz component, 45 Hertz component, 65 Hertz component, 100 Hertz component. Just for example, so we have 5 frequency component. One is the DC component, 0 frequency, then 10 Hertz, 45, 65, and 100 Hertz. So these 5 frequency components are basically contributing to xt, which means, so there are 5 different sinusoids having different amplitudes, and if we sum those 5 components together, you will end up with this xt. Sum of this sinusoidal component gives xt. Okay, so this is the Fourier analysis. So then the maximum frequency component embedded inside this xt is 100. It's 100. F max is 100 Hertz. So then we can basically claim that if you want to sample this xt properly, you need to select the sampling frequency at least 2 times this. If you select your sampling frequency as a 200 hertz, then you can have a kind of a unique xn, which is the discrete form of xt. If you select something else, for example, if you select a 100 hertz signal, so 100 hertz as a sampling frequency of xt, so you cannot basically capture certain features of xt using this xn. Okay, so did I explain this time aliasing before? Did I explain aliasing effects? No? Okay. So let's take two signals. So we have x1t equals to cos 2 pi 10t, x2t equals cos 2 pi 50t. Okay, so by looking at these two signals, we can basically claim that here the frequency is 10 hertz. Here the continuous domain frequency is 50 hertz. So hope it's clear. Okay. I use the sampling frequency as 40 hertz. So now for this scenario, I have two signals. One is the frequency of 10 hertz, the other one has a frequency of 50 hertz. I used the sampling frequency of 40 hertz to convert these two signals into discrete forms. So what happens there? So I'll convert this x1t to x1n discrete domain. So then it would be cos 2 pi. So if you convert it to discrete domain, we found that, so this is basically replaced with f divided by fs into n. So f is 10, fs is 40, and n. Similarly, x2n would be cos 2 pi 50 divided by 40 into n. So if you further simplify this, this is equals to cos 5 over 2n, and this is actually cos 5 over 2. Okay, so we have two signals x1 and x2t, and so we found that they have two different frequencies in this continuous domain. So we select a frequency, sampling frequency as 40 hertz, and try to convert this x1t and x2t to its corresponding discrete domain by applying t equals nts. So the same conventional transform t equals nts. Ts is actually 1 over fs. So then we found that x1t is converted to x1n as cos phi n over 2, and x2 is converted into discrete form with the sampling frequency of 40 Hertz as cos phi n divided by 2. So what happens if you elaborate this more? So this is actually cos 2 pi n plus pi n over 2. So phi n over 2 can be rewritten as 2 phi n plus 2 pi n over 2. So cos 2 pi plus theta gives cos theta. So this is equals to cos phi n over 2. So this is your x1n in discrete domain. This is x2n in discrete domain. So see, so this is exactly same as this. It means if you have two different frequencies in continuous domain and do the sampling using this frequency, so both signals in discrete domain are basically equal. So if you take these signals, if you just refer these discrete signals, one is cos phi n over 2, the other one is cos phi n over 2. Once you plot it in a 2D platform using whatever the software, you can see that both signals are exactly overlapping. So they are exactly same. So we proved it here. So then by looking at these two discrete signals, we cannot simply claim that this signal basically derived from 10 Hertz signal or 50 Hertz signal. So these two frequencies are mapped basically to a single discrete frequency if you use this sampling frequency as 40 Hertz. This 10 Hertz and 50 Hertz is basically mapped to a same frequency in discrete domain if you select this 40 Hertz as a sampling frequency. So this is the one which I explained it in previously. Okay, got the point?
Yes, sir.
Yes, done. Okay. Now, so we found that, so this capital F is basically in between plus infinity and minus infinity. And once you convert it to this discrete frequency, it's basically mapped to this range, plus half and minus half. And again, we found that this with this conversion process, we found that capital F divided by Fs equals simple F. So this is the continuous domain frequency. This is continuous frequency. So this is discrete frequency. So this is sampling frequency. So this is the mapping between this discrete and continuous. And again, we found that, so this maximum is like half. So then F is basically mapped to this value. So this is called the folding frequency. This is called folding frequency. So what do you mean by folding frequency? So it means like that. So we have so this is the capital F range. So this is your simple F range. So what happens here is, so we basically map this range to minus half and plus half. So then if you move beyond this, so again this block is mapped to here. So let's assume. So this is mapped to this block. Then again this block maps to this again. Next block maps to this again. Next block also maps to this. So this Fs by 2 is the folding frequency. So it's like that. So we first map this block to here. Then once this comes, so it's folded on top of this and map it again. If this comes, so again fold it to the same block likewise. So it's like this. So we have this big frequency domain. So we map this block or we fold it on top of this. So then it's like this. So then we fold this third block again on top of this. So then it's like this. So the fourth block again fold it on top of likewise. So we will basically identify this folding frequency Fs divided by 2 and for the entire frequency domain, continuous frequency domain on top of each other. So then it's like you are packing this entire capital F domain on top of the simple F domain. So just pack it. So first identify the folding frequency. Once you identify the folding frequency, you know that where you can fold it. So if this is the case, so this is 0. So this is Fs by 2. This is Fs. So then 3 times Fs over 2. Then another. So then 2Fs likewise. So then what we simply do is we basically bring this one to here, map it on top of the 0 and Fs by 2. So then you take this block and map it on top of the 0 Fs by 2. Then take this one, map it to. So once you map this one, so there may be certain frequency component in those blocks basically align to a single frequency. Did you get the point? So we basically map this entire frequency range to this Fs over 2. So we take this one and pack it here. And we take this one and pack it on top of this. We take this block and pack it on top of this. Take this next block, pack it on top of. So once you pack it on top of this, so these frequencies, this one, this one, this one, and this one may be simply aligned with this frequency. So then F1, F2, F3, F4 may be aligned with this F0 frequency in the range between 0 and 5. It means once you use the sampling frequency, Fs is a constant and process multiple frequency signals, there may be a chance of getting the same discrete signal for this F1, capital F2, capital F3, capital F4, and so on. So those frequency components give the same translation once you use this Fs as a sampling frequency. So all these frequencies basically map to the same frequency. So then you cannot recognize whether this discrete signal is come from capital F1, capital F2, capital F3, capital F4. Okay. If you select your sampling frequency greater than this 2 times the maximum frequency, we can guarantee that there won't be any duplicates or mapping of these multiple frequencies to the same frequency component. Okay. So for example, if you select this 2 times this Fs, so then you can easily identify. So there won't be any overlapping frequencies in discrete domain. So you can just plot, or you can just draw this capital F range and simple F range and see whether if you select your sampling frequency as 2 times F max, so you can't see any signals overlapping on top. So it means like this is your capital F. So this is your F max, and you select Fs as so this is F max, and you select it as here. So this is like at least 2 F max. So then this range is basically in between this. Okay. So once you map it to simple F, so this is basically mapped to this block. No any duplicates due to this selection of this Fs sampling frequency. If you basically select a sampling frequency somewhere around here, so then this folding becomes Fs over 2. So then this block is simply overlap the frequency of this block. So that's why we basically select 2 times F max as a sampling frequency. So then we can guarantee that so there won't be any overlapping frequencies in continuous domain which basically generate the same discrete signal. So then keep in mind, if you want to sample a signal, so you should be very precise about selecting a sampling frequency. How do you select the sampling frequency? So it should be basically at least 2 times the maximum frequency. You should select a sampling frequency as at least 2 times the maximum frequency. Maximum frequency is the frequency components inside your continuous signal. So by applying Fourier analysis, you can simply identify what are the frequency components. So they are in the signal. So if we take one more example, yes. So this is a one small example. So we have signal xt, which is equals to 3 times cos 105t. Okay. So if you are given this kind of a signal, so you should convert into this format. A cos 25 something t. So if you rewrite this to that format, so this is cos 2550 t. So then it becomes 105t. So why we convert into this format, then you can easily recognize this quantity as the frequency of this analog signal or continuous signal. So now it means, so this frequency is 50 hertz of this signal. Okay, so then what is the minimum sampling frequency for this particular signal? So based on this Nyquist theorem or sampling theorem, Fs or the sampling frequency should be at least 2 times the Fmax. So for this particular signal, we know that there's a single frequency component which is aligned with 50 Hertz, contribute to xt. So your maximum frequency component is again 50 Hertz. So then you need to sample this signal at least at 100 Hertz to avoid this previously discussed aliasing types. Okay, so this is your this is the minimum sampling frequency to avoid this aliasing effects which we basically discussed. If you basically sample a frequency less than that one, what happens? So it basically showing some overlaps. Okay. So for example, if you just demonstrate it using graphical form. So let's take this is the frequency range. So you have 0 frequency and this is 50 Hertz. Okay. So the folding frequency. Folding frequency is actually Fs sampling frequency by 2. So here we argue that there should be, you have to select the sampling frequency as 2 times the maximum frequency. Now it's 100. Let's assume like we select 80 Hertz as the sampling frequency. So we select Fs as 80 Hertz. So then the folding frequency become folding frequency equals 40 Hertz, half of this. So it means this is your 40. Now what happens if you fold this entire frequency domain as we discussed previously on top of this domain 0 to 40. So we can simply map this without any issue. So there is another set of frequency component appearing in this block. So if you fold it at 40, so this basically appear here. So this is from 40 to 50 block. So this block appear here. So then if we basically have certain set of frequencies appearing between 40 and 50, so it simply mapped to 0 to 10. So then if we have two signals where one is at frequency in between 0 and 10 and the other one is in between 40 and 50, they basically generate the same discrete signal. So this is the entire logic we built up to now. So then we should be very clear that the folding frequency should be exactly matched with the maximum frequency. Otherwise, there may be some extra blocks like here. There may be some extra block like here will leads to a kind of a collision overlapping. So then this is the sampling frequency. We should set it to avoid aliasing, which we basically explain here. Okay. So then suppose that the signal is sampled at the rate of 200 hertz. What is the discrete signal you can obtain? So now we set the sampling frequency to 200 hertz. Yes, it's so fine because we need to set the sampling frequency which is greater than the 2 times f max. So at least it should be 200, 100. Now we set the sampling frequency 200. So then what would be the signal? So xn equals 3 times cos 2 pi. Here we can put 50 and now the sampling frequency is 200 and this is equals to cos 4 5 by 2n. So this is the ultimate signal. You can get it after this discretization of the sampling process. If you have this 3 cos 100 phi t continuous signal and take the sampling frequency of 200 hertz, you will basically ended up with a signal which is equals to 3 cos phi n over 2. Okay, so the next, set your sampling frequency to 75 hertz. Previously it's like 200 hertz, which is exactly matching with this Nyquist theorem. So here is matching with the Nyquist theorem, or we basically select the sampling frequency to satisfy this Nyquist theorem. But in this case, it's not satisfying this Nyquist or sampling theorem. So we select our sampling frequency as 75. So it's less than 2 times 50 hertz. So what happens for this case? Again, if you sample this original XT using 75 hertz, so this now like as it becomes 3 cos 2 pi 50 divided by 75 and so then if you simplify it, so it's becomes 3 cos 2 pi 2 over 3 and 3 cos 4 pi n over. So this is the signal. You can get it after discretizing this xt equals 3 cos 100 phi t with a rate of 75. Okay. Okay. Now, if you sample this, sampling this 3 cos 100 phi t using 75, so we will ended up with this discrete signal as 3 cos 4 phi n over 3. So if you can find any continuous frequency component which is exactly placing or exactly generating the same discrete signal, what would be that particular frequency? Okay, so let's think about this way. So if you simplify this, so you can claim it this cos. So you can start this 2 pi minus 2 pi over 3. So which is basically give the same signal. So this is again 4 pi n over. So is equals to 3 cos 2 pi over 3. So it means if you find a kind of a continuous frequency which is basically giving the signal, it's exactly aligned or overlapping with this 2 over 2 pi over 3. So it means like if you can, here you have like 2 over 3. So if you can find a kind of a signal having this 1 over 3 ratio, so then it's fine. So then what would be the value which gives the 1 over 3 ratio? It's like 25 hertz. If your signal is 25 hertz, so you will ended up with this 3 cos 2 pi 25 divided by 75 n. Then ultimately it's cos here 1/3 2 pi n over 3. So it means if you select your sampling frequency at 75 hertz, definitely, so that the frequency of 25 hertz is simply overlapping or aliasing with the same frequency signal. So this is a 50 hertz signal. If you take a signal with 25 hertz and do the sampling on 75 hertz, definitely 50 hertz and 25 hertz is overlap. It's clear, I guess, no? So if you draw it, so it's something like that. Now the maximum frequency of the signal is like, so this is your, this is 0. Your folding frequency is now 7. So the Fs equals 75. So the folding frequency is 75 over 2. So it's somewhere here. So this is definitely, this is a 50. And this is mapped to here. So this block is mapped to here. So that's the case, right? If you set the folding frequency to this level, so the maximum frequency is 50 hertz. So this block is simply mapped on top of this. So then this 25 hertz signal is simply alias on this 50 hertz signal if you set the sampling frequency of 75 hertz. Okay, so this is the basic discussion about this sampling theory or sampling. So you should be clear on sampling period and sampling frequency. So if you easily find the sampling period, you can map it to sampling frequency. Fs sampling frequency. So then Fs should be greater than or equals to 2 times Fmax. And you should be able to derive xn using xt by substituting this. You should be able to explain this aliasing effect. And should be able to find out what are the aliasing frequency components for a given fs, given sampling frequency. So these three should be thoroughly learned. How do you set the sampling frequency? Depending on the frequency component inside the signal. How do you convert this continuous signal into discrete domain? By applying this conventional substitution. So then what's the relationship between this continuous frequencies and discrete frequencies, sampling period, sampling frequency, and so on? Then how do you explain the aliasing effects? By mapping this the entire frequency domain in continuous signal by considering this folding frequency, then you should be able to find the aliasing frequencies for given sampling frequency by doing this simple analysis. So if you have any questions, so you can raise now. So if you don't have any questions, so we will discuss this couple of examples of discrete Fourier transform next time. So I'll share one PDF to you. You can go through this document and get refreshed with the sampling process and along with this video. Okay, so hope you can go through and be thorough with these concepts. Okay, so if you don't have any questions, so we'll stop for today.